Chapter 7 Gases, Liquids, Solids, and Phase Diagrams. Section 7.7 The Pressure, Volume, Temperature Phase Diagram. So here is one example. We have pressure, we have specific volume, we have temperature here. The reason we have specific volume here instead of volume is because volume is extensive, specific volume is intensive. We can use molar volume here as well, which is also intensive, or if you specify the amount of the substance, you can even put volume here, because one can easily convert volume to either molar volume or specific volume if you know the amount of the substance. Now let's look at this three-dimensional phase diagram. We have three variables: pressure, volume, and temperature. However, it's really a two-dimensional pressure volume phase diagram at different temperatures. So you can see this is the highest temperature, this is the lowest temperature. So if you collect the PV phase diagram at different temperatures and put them together, you make a three-dimensional PVT phase diagram. At this high temperature, you can see pressure and volume are inversely proportional to each other. Over here, same thing, they are still inversely proportional to each other, but I think there should be some distortion here. Maybe it's hard to see, but there should be a distortion from PV equals RT because temperature is lower. And now right here, this is the critical point. So critical point is important. Below the critical point over here, if you first reduce the volume of the gas, well, you can do so. You can see pressure goes up as volume decreases. Everything's normal, but at this point something really interesting happens. When you further reduce the volume of the substance, you can see there's no pressure change. So this line actually corresponds to constant pressure. How is it possible you are reducing the volume of the substance and yet the pressure remains constant? Okay, actually at this point you are starting to convert the gas into the liquid phase. So from here to here, all you do is you start to convert the gas all into the liquid. So at this point, this substance is completely in the liquid phase, and that explains why you see a sharp increase of the pressure, because if you look at this line, you are compressing the liquid. It's very difficult to compress a liquid with higher pressure. That's why the pressure jumps up really quickly. And we can see more phases. Again, over here, even lower temperature. First you have a gas, and now you're converting gas to liquid. Now, not by changing its temperature is constant. You just compress it. You compress the gas into the liquid. There's no pressure change. You are just compressing the gas into the liquid. So along this line, you actually have a equilibrium between the liquid and the gas phase. And then you have a liquid right here, and you are compressing the liquid. There should be a very significant pressure increase. And then if you further compress the liquid, guess what's going on? The liquid is gonna turn into a solid. So between here and here, you have both liquid and solid phases coexist. And we're assuming actually the density of the liquid is lower than the density of solid for this substance, and that's actually why you can compress a liquid into a solid. And once you have 100% solid, again, if you are trying to further reduce the volume of a piece of solid, it's hard. You need a huge amount of pressure, so the pressure goes up again. And just let you know, this lens should be really small. This is some kind of exaggeration. This lens should be pretty small because the specific volume of solid and the specific volume of liquid should be extremely close to each other. So we have this longer than real line is just to show you both phases coexist. We need some space to put the words over here. All right, and then you may ask, what if the temperature is higher than the critical point? So, for example, this temperature or this temperature, if we keep compressing the volume, keep increasing the pressure, what will happen eventually if the pressure is high enough? When the pressure is higher than the critical pressure, you will get a fluid, and that fluid is the so-called supercritical fluid. The supercritical fluid can occupy the entire container just like a gas would do, and a supercritical fluid has a density much closer to the density of liquid, but much higher than the density of a gas. So a supercritical fluid is like between a gas and a liquid.